So now that we've seen how to calculate the likelihood of a tree on a site and then on a full alignment, it's going to be very straightforward to understand the concept of maximum likelihood tree inference methods. So maximum likelihood framework is the framework under which one tries to find the tree with highest likelihood. It's an optimization problem. We want to find, the model M star, such that the model M star is the maximum over all models M, the model that maximizes the likelihood the likelihood of the best model M star is the maximum over all models of their likelihoods. Okay, so we want to find M star that is argmax of LK of M. So the maximum of the probability of D conditional to M. So this implies to find this maximum, to find this M star, it implies to look for several M's. Okay, several models M, so several trees. And this problem is an optimization problem over an infinite space, so that's why we are going to use three alterations, NNISP or TBR, to modify the topology and recalculate the likelihood and trying to find the best likelihood. By the way, you see that in order to calculate the likelihood, we need branch length. So I've not shown how to optimize branch length, but there are some methods that have been developed in PAML, PhiML, RaxML to try and dilatate or shrink branch and then calculate the new likelihood. Shrink locally one branch, try to find an optimum on one branch, and then move to the next branch, try to find an optimum, etc., etc. There are many different methods, but it is important to know branch length, and part of the work of these software, PAML, PhiML, RaxML, I need to cite these three, is to optimize branch length. Okay. So it's not only the topology is optimized trying NNI, SPR, and TBR moves, and there are some algorithms of iteratively improving locally branch length to try to improve the likelihood of the model. Let's turn to Bayesian methods. Okay, that's the fourth and last class of three inference methods we're going to see. And the concept of likelihood of a model is also central in Bayesian inference methods, but Bayesian specialists adopt a different viewpoint. Let's see, and let's first start with remembering Bayes' theorem. It's a theorem linking conditional, marginal, and joint probabilities. This is the joint probability of A and B happening together simultaneously. The probability to have A and B is the probability of A conditional to B times multiplied by the probability of B. Okay, and the roles played by A and B are symmetric here, so you can also get that it's the probability of B conditional on A times the probability of A. And if you use this right hand side of the first equal sign, and you move this probability of B to the denominator on the right hand side, that's what you get. Probability of A conditional on B is equal to probability of B conditional on A times probability of A divided by probability of B. Okay, and let's apply this Bayes theorem to phylogenies. So when we talk about phylogenies, we have instead of A and B, we're going to have the data and the model, and let's play with these a little bit. So here I've started with probability of M conditional on D is equal to probability of D conditional on M times probability of M divided by probability of D. So in Bayesian terms, so remember this probability of D conditional on M is the likelihood of the model. Okay, likelihood of the model is the probability that the data has been generated by this model. And in red, we have new terms that are introduced by the Bayesian viewpoint. We have probability of M knowing D or conditional on D. This is what is called the posterior probability of the model. Posterior probability. So that's the probability of M a posteriori, meaning after having seen the observations, right? And the Bayesian viewpoint is that you had a probability of the model a priori before you saw the data. So the idea of the Bayesian framework is that the data, the observation of the data modifies your belief concerning the model. Okay, the model, the generative model, was always there, but you had a certain prior probability on it before you saw the data, and then the fact that you see the data gives you a posterior probability, right? And the viewpoint of the Bayesian framework will be that what we have to optimize, what we have to maximize, is not the likelihood of the model, is not this probability of D conditional on M. What we have to optimize is the probability of the model given the data. And that makes sense. This viewpoint makes sense. But we'll see that computationally speaking, it's very demanding. And we leave for the next slide what we have: the denominator, the probability of the data here. It's very difficult to calculate as it is. Probability of the data, we don't know. We just got the data. So we observe the data. What do you mean that I have to calculate the probability of the data? So let's see this denominator. It's in fact a sum of joint probabilities, or we can express it as a sum of joint probabilities over all models. Okay, we have a certain number of models, possibly infinite, and if I want to calculate the probability of the data, I can say, oh, it's a probability to have the data and the model 1 jointly with the model 1, okay, joint probability D and M1, plus the probability to have the data and model 2, okay, plus the probability to have the data and model 3, etc. Okay, you sum them because these joint events are separate. Okay, you cannot have at the same time D and M1 and D and M2 because M1 and M2 are two different models. So it's the sum of the probability of D knowing M prime and over all M primes, and this, using a trick, you can also rewrite this as sum of the probability of D given conditional on the model M prime times the probability of the model M prime. And this trick is simply applying the Bayes theorem, okay? From this to that. Right. So we have expressed here the probability of the data as a sum because we had no clue. We didn't know how to calculate this, but now we express it as a sum of these kind of terms, okay? But what makes the situation a bit more complex is that the space of all the models here is not discrete, okay? So you cannot say I sum over the models M prime taking their values into a discrete, countable set. It's not like this, it's a continuous space. So we would write things like this using instead of a sum and an integral. Okay, so that's what we get. And if we plug this into our formula for the Bayesian framework on phylogeny inference, what we have is this. So posterior probability is the target to optimize. Okay, we want to optimize this to find the model with the highest posterior probability. Here we have this in the numerator, and remember the denominator was PR of D, here the probability of D, and we rewrote it as an infinite sum of probability of D knowing M prime times probability of M prime. We have this, right? And I replaced the probability of D knowing M prime by likelihood of the model. So LK of M, and here we have a sum of an infinite sum of these likelihoods times probability of the model. So we see that the numerator and the denominator have the same kind of shape, only that here we have one element, and here we have at the denominator we have an infinite sum of same type of elements. So the final Bayes formula comes with its challenges. I highlighted these challenges here on this slide. So likelihood, okay, we know we have this good old Felsenstein pruning algorithm, so we are able to calculate likelihood. But now what's the probability of a model? A priori, the prior probability of a model, okay? We have to evaluate this here. We also have to evaluate them here. So each model should come, each phylogenetic tree should come with its prior probability. What's the probability a priori to get this model? Second problem, so how to define the prior probability of a model is a problem. Second problem is that we have lots of LK of M prime to calculate, okay? We have a potentially infinite space of phylogenetic models. So even if we want to approximate this this infinite sum with a finite sum, we have to sample our space of phylogenetic models, and we have to make sure that somehow we approximate not too badly, meaning that with a finite sum we try and cover as thoroughly as possible the space, this infinite space of phylogenetic models. And if we do this, even if we transform this infinite sum into a finite sum, approximating it, we'll have a huge number of likelihood calculations involved for the calculation of a single posterior probability, okay? So it's very computationally intensive. And that's the main disadvantage of the Bayesian framework. So, priors on trees. First problem to solve. Let's have a look at this. How to define the prior probability of a model. Well, different strategies have been devised, and the first simple one is to use a flat or uninformative prior distribution. All trees have same prior, okay? So you can, in a way, simplify here by this probability of the model. If all of them have same prior, if all your models have same prior, it's okay. It leads to simplifications. We can have both this Markovian process of speciation, and then from this you infer what's the probability to have this topology or this certain model. You have a generative process to generate models, and then you assign to each of the models their probability in this framework of this generative framework for topologies. You can have priors using an arbitrary distribution and branch length, etc., etc. You have different priors, but there is a problem in selecting the prior, and none is completely satisfactory. So the people who are advocates of the maximum likelihood framework, that's one of the criticism they have against Bayesian methods. They say, okay, look, if you're using the Bayesian viewpoint, you have to use priors, and no priors are satisfactory. So, yeah. And on the other hand, the Bayesian viewpoint is that these priors don't matter much. You can select one type of prior or another one. Ultimately, it won't affect much the results you get in terms of it won't really modify what's the topology and the model, the whole phylogenetic tree that maximizes the posterior probability. And other problem, sampling the space of trees. So we have somehow, because we don't know how to calculate infinite sums with a computer, we can only calculate finite sums, so we'll have to try and sample the space of possible models. And for this approximation, for the approximation of this by a finite sum to make sense, we have to make sure that we cover lots of the space and that the points or the models that we don't include in our finite sum are models that would lead to a very low value here of likelihood times prior, basically a low value of the likelihood. So we have to sample intensively the space of all phylogenetic models and calculate the likelihoods, corresponding likelihood, and make sure that we leave out only in a way we leave out the likelihoods that are very small. So the idea of the Markov chain Monte Carlo methods is to go at random and long enough to travel at random in the space of all possible models, of all possible trees, and long enough in this likelihood landscape to cover as best as possible the areas of good-ish likelihood, because we approximate this sum, this infinite sum with a finite sum, and as I said, we want to leave out of this is a sum of positive numbers, right? A probability is positive, a likelihood is also a probability, a product of positive numbers is positive, but we want to make sure that in this sum, the ones we don't include, the infinite number of points of models we don't include, are the models leading to a likelihood that is negligible. So we want to wander at random in the likelihood landscape. Likelihood landscape is the landscape of all models, but imagine that each model gives you an x and y coordinate, and your landscape, the elevation gives you, or the elevation of points, the z coordinates, corresponds to the likelihood. So you have like a landscape with valleys and mountains, and you want to make sure that you sample all the mountains, the points where the likelihood is high, the areas of good-ish likelihood, okay? And also the areas of likelihood that is not too good, because it's important to include them in your sum. So ultimately, we want to get a reasonable image of the whole likelihood landscape. We can afford to neglect the points of almost zero likelihood, but not the others. So an MCMC example is the Metropolis Hastings method. So imagine you're here, you're trying, you throw many small agents, individual agents, and these individual agents have a rule that they follow in order to know where they're going to go next, where they jump. Okay, they're going to jump from one point to another, and on the x-axis, and they're going to sample the likelihood where they are. And the idea is that we want, with a few robots, in a way, to achieve a good coverage of all the parts of the landscape that are high. Okay? So the MCMC method process is a process of kind of random jumps and select your jump if you've gone to a point that is higher or same altitude, and if you've gone to a point of to a lower altitude, you are going to have higher chances to discard this jump. Okay, so it's a technique. You can read the slide in detail, but it's a technique that probabilistically tries to achieve good coverage of the high points of the landscape without completely rejecting the jumps that lead to smaller or to lower altitudes. And what is very important is that you have several agents, several small robots, wandering in the same landscape. And at some point you say, okay, it's fine. You have been surveying the territory. Give me your reports about all the points where you've been. Okay, and it's inspired, or it has inspired techniques that belong to the field of swarm intelligence. And when we look at colonies of ants, they also try to survey a territory, and some go at random. Most of them follow the path that would be the hill climbing path, but some other ants, if we take this analogy, would also, in a fewer numbers, would also explore the low areas, in the hope that they from these low areas they will maybe spot another maximum that is further, that we wouldn't see in this graph. For instance, if there were a further local maximum on the right, it's important that we allow exploration of this dip, so that maybe the agents that are exploring this dip will find that they can climb and go up also on the right of this slide. Let's have maybe the last break soon. No, after this graph, this slide, sorry. So some MCMC refinements. So you understand that we'll have agents, okay, jumping from one point to another. And here the agent is called the chain, okay, because yeah, it's called the chain. So the chain linking together the different steps. Okay. So this slide here shows you an example of the exploration of a space where you have two peaks, two mountains. You have here a round mountain. These lines are cores, I think, lines of equal altitude. So you understand that here we are on the plane, it's low, and here we have a higher altitude, which will be, in our case, a higher likelihood, and here a higher likelihood also, and this is a smaller peak, okay? But maybe the values in terms of likelihood are same here than here, or even higher. So we have our small ants, and we want them to explore this territory. They start somewhere, and we want them to explore this territory, and what we want is that they spend lots of time exploring the areas that are of high altitude, and we want them to explore, not to spend too much time in too much of their time in the areas of low altitude. And we want to have an automatic way to perform this exploration. So on top we have only one cold chain, and here this is the number of steps that have occurred. So here you have 100 points, here you have 1,000, and here 10,000. Let's imagine you have one chain, okay? Remember your ants, or your ant, because she's alone and she's jumping from one point to another. This ant or this agent is going to jump from one point to another, accepting favorably always the jumps that make her go higher, and accepting with lower probability jumps that make her go to lower altitudes. So if your ant starts somewhere here, chances are it will find that, okay, here we have a space of high altitude, and the ants will tend to spend more and more time in this space, okay, right? We have points here because in the Metropolis Hastings algorithm, it's not completely forbidden to jump from a point of high altitude to a point of lower altitude. But it's this jump is accepted with a lower probability, right? This is not possible in such an example for this ant to explore, to jump as far as this second, as to explore this second peak, right? In order to make it able to explore this second peak, you have tricks. You can increase the size of the steps in the hope that you will be able to jump straight from one point here to one point there. You can increase the acceptance probability for jumps going to a lower altitude, etc., etc. There are tricks. But we see that it's not the best in this framework. When you have just one chain, it's not going to work very well, and in most cases you won't be able to explore this peak. One solution would be to have many chains or many different agents, many different ants, and have them start randomly. So if we have one ant that starts here or starts close to this peak, chances are that this ant will lead to a good exploration of this space, right? Here we introduce an example still using only 2 chains, not completely random. We have different expected leap length. So as I said, we have one chain that jumps fast and far and is a bit crazy. That's what we call the hot chain. The cold chain is conservative. So the cold chain is used to explore more locally, and you'll see that the hot chain with long steps is less conservative. And what's the nice trick that people in this field of Bayesian inference techniques have used is that from time to time you swap the cold chain and the hot chain, and it's beautiful. It means that you just artificially, I mean, from the viewpoint of your program, you just say at some point, okay, these 2 chains explore in parallel, right? And at some point you say, okay, now the current position where the cold chain is, I place my hot chain there, and the current position of the cold chain, of the hot chain, becomes the current position of the cold chain, right? And if you do this, you see that after leaving the system explore for 10,000 steps, you have this map here, where you see that the cold chain has been used to explore locally, and it has explored the 2 tops, while the hot chain has been used to explore more aggressively, more randomly, points of the space where that belong to the planes, right? So that's what we do. If we're interested in exploring the space of points of high altitude, we understand that we have to discard the beginning of the exploration, because the beginning of the exploration for any chain was too dependent on the point where you started your chain, right? So a chain that started here, for instance, spent lots of time exploring a region of the likelihood landscape that has little value. So another technique in MCMC is to have a burnout initialization of your chain that we just discard. Okay, so these examples show you how the MCMC work. You have to understand that each point here corresponds to one calculation of a likelihood. Each point corresponds to a different model. So running a chain during 1000 steps means that I have to perform 1000 calculations of a likelihood. So it's quite an expensive process in terms of computation time. Let's have a final break here.